In addition, the first law thermodynamics is used in the understanding and design of heat engines such as steam engines, internal combustion engines and gas turbines. So heat engines are all, it will convert the heat energy into mechanical work. Okay, so within the system, if you want to study the heat balance, energy balance, the first law thermodynamics is used. Not only that, to design, so I said now, so heat energy must be converted into completely mechanical work. But if it is not happening, so how to design my equipment so that it will completely convert heat energy into mechanical energy. Okay, so this is about the heat engines, how the first law thermodynamics is helpful to design and to study the heat engine. Completed. So what is the next one? Refrigeration and air conditioning. Okay, what is the refrigeration and air conditioning? Kranti, Rupa, Kranti Kumar, and the next Nagaraja. What's your name? Sanjay Kumar. Yes, Sanjay Kumar and Rupa Kranti Kumar. What is the refrigerator? Do you use it? What is the purpose? To cooling. Why do you want to cool? Preserve the food to inhibit the growth of microorganisms so that food won't be spoiled. That's the purpose. So what is the air conditioning purpose? Sanjay Kumar? Air conditioning. To purify the air. Why do you need air conditioner? You need filter is sufficient now to maintain the room temperature always. Whatever the temperature outside, whatever the temperature, maybe for example in winter, outside temperature is very low, but always we want to maintain the room temperature, that is 25. In the summer, outside temperature is very high, but still we want to maintain the room temperature. It is conditioning means in the winter it will produce a high temperature heat. In summer, it will produce a low temperature heat. Okay, so that is called air conditioner. Now, only it won't work. So it won't work in summer only. It will work also in the winter also. It will, okay, that is the air conditioner. What's the purpose? You want to, our bodies are very comfortable to survive in the room temperature. That's the purpose. Okay. So how the refrigeration will produce in the to cool the substances like food, how the low temperature fluid is generated, low temperature is generated. Do you know anything about it? There will be a compressor. Okay. Very good. It may not be correct, but you tried. Very excellent. Air conditioning. So you want to cool this room. So how do you want to cool? For example, now cool or hot? Moderate. But I want to increase the temperature of this room. How can you do that? Now the temperature is 25, but I want to increase to 35. How can you do that? Just supply the heat. Okay, heat. Hot fumes are hot air inside it. That will be sufficient. How to produce a hot air? How to produce a hot air? How to produce a hot air? Do you have room heater? Do you know? So room heater will just coil is there that will coil the electrical energy into heat energy. So when you put the fan, the air is blowing, that the air is actually room temperature, that air molecules will go through this heated coil, so that the heat is absorbed by this air molecules and they will be heated up. So that we get the hot air. So that gets sent to the room. So it is that room temperature will be. Okay, now I want to cool to around 50 degree temperature, because we are suffering from the room temperature. So it will be cool. So we will be very happy. So how can you do that? It will take hot air. So hot air is completed. Now I want to cool the room. How can you do that?
By taking outside other factors regulated, you take the lower temperature and produce the same towards the lower temperature and compare.
I said you want 50 degree temperature in the room. How can you do that? You send the cool air. That's it. How can you do the cool air? How can you send the cool air? Initially, hot coil use. Now use the cold coil. How can you produce the cold coil? You send a very low temperature fluid through this coil. Then, which is the air is coming, that will be heated. The cold coil, and then the air is cold. Now you can send that into the room, so that it will be done. Very simple. Okay, but very simple. But how to design it is very important. Economically low cost, efficient one. So see, you are seeing that air conditioning is a very simple process. If you want to increase the room temperature, just heat up the coil, which have a very high resistant metal. Just connect the electricity, because of the resistance is there in the metal. Because of the flow of electrons are hindered, so that because of that will convert it into heat. So means the coil is being heated up. You just send the air, just blow the fan. That will be that will touch the air molecules will contact with this hotted coil, and air is heated up, and you can send that hot air into room. In the same manner, if you want to decrease the temperature, just in place of hot coil, you just take the cold coil, so that through the coil you send the low temperature fluid. Same thing will happen. There is no much difference. But design is very simple, na? Now in this case very simple, but economically low cost and efficient one. It cannot be like it will take high amount of energy, but generating very low amount of work. Means room temperature is. If you want to increase the room temperature around 30, it will take very long time. Then it's not an efficient one. If you want to decrease the room temperature around 15 degree temperature, it will take a whole day. Then you never be cooled, and you never be room temperature cannot be getting down until the full day. So then it's not an efficient one. How to design that? So means thermodynamics will help you to design. It means whatever the heat is I am supplying has to be reached to the room perfectly. So what are the losses are there? Because energy cannot be destroyed, cannot go vain. So if it is going vain, somewhere losses are there. How to overcome that? How to overcome the losses? So that how can I design the equipment such a way that whatever is generated is going to the room like that. Okay, so that way. So like it will be useful. So now please write refrigeration and air conditioning.
Sir, whatever coolers,
Please it, both are same.
we are using a motor, right? And you are saying coil.
Cooler means what is cooler means?
Cooler, sir.
We use in the summer time. Both are same only. Electrical energy converted into the mechanical energy. When the mechanical energy, water is there, the water is circulated through the side by. Yes, through the which is there through the grass. When the water is circulated, the water is at generally room temperature, low temperature. So the outside the air is very high temperature. So it may be around 40 degree temperature. The air means here oxygen, nitrogen, whatever the compounds are there in the air, those molecules at a very high temperature, like a 47 degree temperature. When these 47 air molecules will pass through the air, energy exchange, the water and air. So that and the fan is there, the fan will push towards us. So we will get the cool air along with the small amount of water vapors. Because water vapors are because of not water vapors we are getting cool. Because of the air is cool from the 47 to the around 25 degree temperatures are lesser. Okay, that is it. The refrigeration in air conditioning systems which transfer heat from a cooler space to a warmer space using work input. Refrigeration in air conditioning systems which transfer heat from a cooler space to warmer space using work input. What is the first point meaning? Like in refrigeration, you place some material, like for example, you place the apples. So apple generally they are at room temperature. So means at a warmer temperature. Means the energy is transferring from the because the fluid which are sending to the refrigerator at very low temperature. So the energy is transferring between the fruit and the very low temperature fluid. So energy is exchanging. That's the reason. The heat transfer from the cooler space to warmer space. From the cooler to warmer fruits or whatever the food. So using the work input. These first law of thermodynamics helps to analyzing the transfer of energy. How can you transfer effectively from the low temperature gas to the high temperature food? So that when the energy transfer is done effectively, so that fastly the temperature, the food temperature will be cooled down, then the food will be preserved in time. Otherwise it will take long time, otherwise it will be wasted. That is the efficiency. 4 star, 5 star, you know that na? What is the meaning of 4 star, 5 star? Do you know, have you seen that on the fridge, 5 star fridge? They denote the efficiency of the, denote the efficiency and power consumption also. Power consumption means it will take low power consumption but will do the quickly. Okay, high efficient. So that is the thing. Okay, next one. What is the next one? Third one? Chemical reactors. Yes, Bhavani na? Akila, somebody has to say. Sorry. Akila, you can please repeat the name? Sangeeta. So can you both stand up? Come, sit here. Take your pad and notebooks. So please discuss. Okay? Chemical reactions. How the chemical means how these chemical reactions. The first law of thermodynamics is helpful to understand the chemical reactions. We sit together and now tell. Chemical reactions. How the first law of thermodynamics will be helpful to study the chemical reactions or analyze the chemical reaction and to design the chemical reactions. How? Sangeeta and Alekhya na? Akila. Guess it. I'm not asking question and answer. Just guess something. Okay, what is the chemical reaction? Chemical reaction. Stand up, please. What is the chemical reaction? Chemical reaction. It gives the reaction. Chemically, some transformation is there. That is called chemical reaction. Physically, some transformation is there. That is called physical reaction. What are the physical reactions? Yes, please. Shavantina, Sushma, what is your name? Sudhishna. Please don't disturb others. Okay? Please, I am requesting you. Yes. So, what is the chemical reaction? Chemically, some transformation is taking place. Chemically, some transformation is taking place means protons are changing, electrons are changing. Okay? So, when the protons are changing, when the electrons are changing, there is a energy change because, for example, two molecules are there with some chemical bond. When the electrons or protons are changed, the bond is broken. When the bond is broken, some energy is released. Okay? So chemical reaction means bond is formation or bond breaking. When the bond formation you need some amount of heat energy, bond breaking some amount of heat energy released, that is called exothermic reactions, endothermic reactions. So to study the exothermic reactions, endothermic reactions, how the first law of thermodynamics can be is used? Where? Huh? Industry only, but how? Means I supply some heat energy to the chemical A and B, both are mixing, so bond is formed. Heat energy is converted into the chemical energy. Yes, here heat energy is converted into the chemical energy. Whatever the heat energy is supplied has to be converted into the chemical energy. Is it happening? No. Why it is not happening? So what are the things I need to do? How can I design the chemical reactor so that whatever the amount of heat energy I have given converted into the chemical energy? Okay, that way it will be useful. Okay, understood? Yes. Now next one, please, chemical reactions. In chemistry and chemical engineering, please write, in chemistry and chemical engineering, the first law is applied to study and analyze various chemical reactions. In chemistry, chemical engineering, you write comma, and pharmaceutical engineering also. PR firstly. In chemistry, chemical engineering and pharmaceutical engineering. Chemistry, comma, chemical engineering and pharmaceutical engineering. You are now listening. First one. In chemistry, comma, chemical engineering and pharmaceutical engineering. The first law is applied to study. And analyze various chemical reactions. Okay. It helps in understanding the energy changes associated with the chemical reactions. It helps in understanding the energy changes from the heat energy into chemical energy associated with the chemical reactions, including heat transfer and work done. Here, work is a chemical reaction. Heat transfer and work done. Pay the money and you get the factors online, offline. Very much useful, especially for engineering. You are interview, so you have a mathematics. What is the actual English? Is there mapping that means using the mathematics you need to solve the problem. For example, problem is yes. The problem is room is getting up. Is the problem? How to deal with the efficiency? It is the temperature of the solution with the efficiency. So that is the problem. So now this problem will be in the matter. Means you try to solve what is that numerical code. It is not a C language code. It is a numerical code. Means some numerical methods are there. Mendelssohn method, Fischer method, interpolation, extrapolation. So numerical methods are there. Using those numerical methods, we write the code in that way. Just mathematics. When you write that code, you apply the values in code, it will We solve whatever the complex problem is simulated in the MATLAB and we solve. So that way it will be useful. Non-coding software or MATLAB? Pardon? Matrix laboratory is called MATLAB only, but when you abbreviate full name it is Matrix laboratory. Means the lab, the matrix lab. Means in a big test tube, we add some two chemicals. Here we add some matrix to the test tube and some results will come. So that is matrix laboratory. This is a platform which will be useful to study the numerical analysis or numerical related problems. To solve the problems, it will be useful. This is a fundamental thing only, but very high complex problems we cannot do by paper and pen. We cannot do that. So like a 3-dimensional heat transfer, we cannot do with the paper and pen. It is not possible. So then, in this case, if this MATLAB is a platform, it will solve and will give the results. So that will be, and first thing is problem solving, optimization, especially for our carbon situation, it will be useful for optimization. Optimization the process, optimization the equipment, optimizing the equipment. And in the other branches like signal processing, data analyzing, data structures, and these are all in the introduction class. We will discuss how where it will be useful, how it will be useful. Okay? 2 classes, just 2 classes. This is lab only, it's not class. I don't teach anything, you have to teach to me. Means you have to do, I'll just give the problem, you have to do in your own computer, you have to write the code, or just execute it. You have to show to me, that's the one. In the classroom, we can go to the chemical engineering lab also. Chemical engineering, for also some computers are there, we can do there also, but it is not sufficient at a time. 2 batches can be, but it cannot be like that. You cannot split the batches, you don't have that much capacity and time also. Okay. So now what's the next one? Thermal power. So thermal power means what are the thermal power? What are the thermal power? Karishma and Srilata and Karishma. What are the thermal power? What are they? What is the purpose of that? Purpose of them? To produce the, from where? Heat energy. From the heat energy, they produce the electrical energy. Very good. So how this first law of thermodynamics is helpful to study the thermal power or thermal stations.
So when we are getting heat energy by any means, by using any energy, we have to no heat loss. And in this criteria,
so now heat energy is converted into electrical energy. So are you able to generate from these power stations or power plants? Are you able to generate whatever the amount of heat you supplied? Is it completely converted into electrical work or electrical energy? So that how to design them? You want to do it. How to design the power generation so that whatever the amount will be absorbed completely and completely maximum efficient. The process is maximum efficient so that it will use the maximum efficient electricity. Okay, in that case it will be useful. Yes, next one. So thermal power plant. Please write thermal power plants. Thermal power plants. Thermal power plants. Thermal power plants. We generate electricity by converting heat energy into electrical energy. Thermal power plants. We generate electricity by converting heat energy into electrical energy. So, what is this plant? What is this?
Nuclear power plant.
Thermal power plant. Nuclear is the source. It can be coal, it can be nuclear, it can be in petrol also. Okay. So what are they? These four things are there, na? This is called chimney. Very long one. What do you call these four? Do you know anyone? Anyone has visited this plant?
Ramagunda Power Plant.
Ramagunda Power Plant. Have you visited that?
I've seen it while going.
Right. Have you inquired what are they? Do you find them that very big one? Towers? These towers. Did you notice them?
Yes, sir.
What are they? Anyone you have inquired anyone? You have not inquired. So what are the things is coming? You see down here.
Whatever byproducts we are getting, we are releasing into the air.
Whatever the waste material which are coming, they are sending into the air. That is wrong, 100% wrong. According to the law, you cannot send like into the air. There is a chiller. So natural chiller, natural convection based on the heat transfer is there, na? In that heat transfer, convection is there. In that convection, two type of convections are there. What is the first one? Natural convection. So this is a natural convection chiller. Okay. So this shape is there, na? Very big one, low. So when the very big one is there, means the size is more, means velocity is low. When the velocity is low, means pressure is high. From here the velocity is very high. When the velocity is high, means pressure is low. Means always air want to flow from the high pressure to low pressure. Low pressure. So here we can see some openings are there. Air will enter into this because the here low pressure is there because of the wide space. Here less space is there. That's the reason velocity is more. That's the reason pressure is low. High pressure to low pressure. So that air low pressure to high pressure. That's the reason air want to down is the high pressure, upper is the low pressure. So air want to flow from the high pressure to low pressure. So it will continuously flow, natural flow. From the middle, the heated water, the temperature, because the water is converted into the steam. That steam is useful to run the turbine. After that, again it is converted to the water only. After work, the water is not at room temperature. So it will be somewhere at 40 and 50 degree temperature. We need to cool them. So how can you do that? Using this chiller, using just sprayers. The water is at room very cool temperature and the water is at high temperature. When they contact each other, the energy transfer taking place, so that water is coming down with a low temperature water, the air is going up with a high temperature. That's the water, just hot air only, nothing else. So like that is a natural way without doing any pump, without using anything. So the water is cooled. Then after cooled water will again be circulated into boilers to generate the steam. After the generated steam will be used to generate to run the turbine. So this is the process. Okay. So that way, so this when you go next time when you go in, just you can see that you can just go nearby that and you can see that there are the openings are here. You can see the process. So that when you know the science, so the process will be very easy. Otherwise you need to suffer like a illiterate. So okay. So they don't know that they repeatedly they are doing. By experience they will know. But the science will help you in the beginning. From the beginning you can do things complex into simpler. Okay. So that is about thermal plants. Completed this one. Next one. What is the next one? Combustion chamber. So combustion chamber. What is the combustion process? What is the combustion process? Rosie and Sushma. What is the combustion process? Combustion. Burning of coal and something else. As a coal wood, okay. Burning of coal. That is not combustion. That is yes, that will be not combustion. Hydrocarbons. In other words, burning of hydrocarbons in presence of oxygen. And it will the products are very less amount of carbon dioxide and water, but high amount of heat energy. That is called combustion. Our main product is the heat energy. Please use it. Heat energy. So this is called those reactions are called combustion process. Means using the hydrocarbons when you in the presence of oxygen, when you burn them, lot of amount of heat energy released, but very few amount of carbon dioxide and water will be released. So if that is the case, if there is any processing like that, then you can call them as a combustion process. Generally hydrocarbons only used because high amount of energy released, low amount of water and carbon dioxide will be released. Any other thing, that is not the case. For example, you burn the tire. So what amount of energy released? Well, less amount of heat energy but more amount of carbon monoxide. Not carbon dioxide also, less amount of carbon dioxide but more amount of carbon monoxide and less amount of water. So it cannot be combustion process. With combustion process, the main aim is to generate the heat energy. Okay. So in this case, how the first law of thermodynamics is helpful? Please write combustion process. The first law is crucial. Ramesh will write. Ramesh, you dictate, they will write.
The first law is crucial.
Slowly, so they will write. You also write parallel. Please write parallelly and dictate.
The first law is crucial in analyzing combustion process. In analyzing combustion process, such as those occurring in engines, and furnaces. Second point, it helps in understanding the energy released during combustion. And the associated changes in temperature, pressure and value.
Thank you. Okay, now both of you. So what is the energy is converting? Which energy converting to which form? Both of you. Which energy? Because energy is converting something. So which energy is converting to which form? Which energy? What is that energy? Chemical energy. Very good. Chemical energy converting to heat energy. Excellent. Please see. So yeah. Please give big hand. Don't type. Nice. Okay. So with the second law of thermodynamics applications. What are the second law of thermodynamics applications? What is the first second law? What is the second law? Entropy. That is absolutely wrong. Entropy increases with time. Very good. What is the entropy? Nitin. Okay. Disorderliness or randomness of the system will increase continuously. Okay. So we have still 20 minutes are there. So actually, speaker. Okay, Teresa? First. Okay. So what is the entropy? Randomness, disorder. What is the randomness or disorder? Anything? Just I'm guessing. You know anything? Randomness or guess. Is it? Are they sitting randomly or are they sitting in a orderly? Order. So what is the means? They are sitting 2 by 2 in an order manner. The position and the direction same. And the position there are, for example, there is a position, they are not changing, and direction towards the maybe it is the east side. Okay? Yes. So now what is the randomness mean? What is the randomness means? What is the randomness means? In this, according to this example, what is the randomness? Pardon? This example. This is a or the students are sitting orderly. Randomness means changing a position. Changing the position, Changing the position. Randomly means sitting randomly, there is no order. For example, someone sitting here, someone is sitting there, just maintain. Otherwise, there are sitting 3 members sitting together. Here 2 members are sitting, or 1 member is sitting. There is no order. Here, but base 2 members are sitting. So orderly they are sitting. Randomly means there is no particular order. For example, if I want to go from here, there are sitting 3. After that 1. After that no one is there. After that many are there sitting together. So that is the randomness. Okay. So my entropy is this randomness, this order is there, this order is continuously changing with the time. For example, when I leave the classroom, immediately what will do? The randomness will increase. This randomness will increase in the system continuously. Okay? To understand that, so just a small video is there. So we actually entropy is very complex topics, but it is not thing that we can understand, but we need to put more concentration many times, then only we can understand. Please listen carefully, okay?
There's a concept that's crucial to chemistry and physics. It helps explain why physical processes go one way and not the other. Why ice melts, why cream spreads in coffee, why air leaks out of a punctured tire. It's entropy, and it's notoriously difficult to wrap our heads around. Entropy is often described as a measurement of disorder. That's a convenient image, but it's unfortunately misleading. For example, which is more disordered, a cup of crushed ice or a glass of room temperature water? Most people would say the ice, but that actually has lower entropy. So here's another way of thinking about it, through probability. This may be trickier to understand, but take the time to internalize it, and you'll have a much better understanding of entropy. Consider two small solids, which are comprised of 6 atomic bonds each. In this model, the energy in each solid is stored in the bonds. Those can be thought of as simple containers, which can hold indivisible units of energy, known as quanta. The more energy a solid has, the hotter it is. It turns out that there are numerous ways that the energy can be distributed in the two solids and still have the same total energy in each. Each of these options is called a microstate. For 6 quanta of energy in solid A and 2 in solid B, there are 9,702 microstates. Of course, there are other ways our 8 quanta of energy can be arranged. For example, all of the energy could be in solid A and none in B, or half in A and half in B. If we assume that each microstate is equally likely, we can see that some of the energy configurations have a higher probability of occurring than others. That's due to their greater number of microstates. Entropy is a direct measure of each energy configuration's probability. What we see is that the energy configuration in which the energy is most spread out between the solids has the highest entropy. So, in a general sense, entropy can be thought of as a measurement of this energy spread. Low entropy means the energy is concentrated. High entropy means it's spread out. To see why entropy is useful for explaining spontaneous processes, like hot objects cooling down, we need to look at a dynamic system, where the energy moves. In reality, energy doesn't stay put. It continuously moves between neighboring bonds. As the energy moves, the energy configuration can change. Because of the distribution of microstates, there's a 21% chance that the system will later be in a configuration in which the energy is maximally spread out. There's a 13% chance that it'll return to its starting point, and an 8% chance that A will actually gain energy. Again, we see that because there are more ways to have dispersed energy and high entropy than concentrated energy, the energy tends to spread out. That's why if you put a hot object next to a cold one, the cold one will warm up and the hot one will cool down. But even in that example, there is an 8% chance that the hot object would get hotter. Why doesn't this ever happen in real life? It's all about the size of the system. Our hypothetical solids only had 6 bonds each. Let's scale the solids up to 6,000 bonds and 8,000 units of energy, and again start the system with 3/4 of the energy in A and 1/4 in B. Now we find that the chance of A spontaneously acquiring more energy is this tiny number. Familiar everyday objects have many, many times more particles than this. The chance of a hot object in the real world getting hotter is so absurdly small, it just never happens. Ice melts, cream mixes in, and tires deflate because these states have more dispersed energy than the originals. There's no mysterious force nudging the system towards higher entropy. It's just that higher entropy is always statistically more likely. That's why entropy has been called time's arrow. If energy has the opportunity to spread out, it will.
So, understood? Anything understood? Anybody? So now we'll ask, what is the video is explaining? So explanation part. We will tell last two. So, did you understand anything? Have you understood anything? Little bit. Little bit. Anything? No. Yeah, please explain. You said yes or no? You said no. Yeah, that will tell. So once more, okay then.
There's a concept that's crucial to chemistry and physics. It helps explain why physical processes go one way and not the other, why ice melts, why cream spreads in coffee, why air leaks out of a punctured tire. It's entropy, and it's notoriously difficult to wrap our heads around. Entropy is often described as a measurement of disorder. That's a convenient image, but it's unfortunately misleading. For example, which is more disordered, a cup of crushed ice or a glass of room temperature water? Most people would say the ice, but that actually has lower entropy. So here's another way of thinking about it, through probability. This may be trickier to understand, but take the time to internalize it, and you'll have a much better understanding of entropy. Consider two small solids, which are comprised of 6 atomic bonds each. In this model, the energy in each solid is stored in the bonds. Those can be thought of as simple containers, which can hold indivisible units of energy, known as quanta. The more energy a solid has, the hotter it is. It turns out that there are numerous ways that the energy can be distributed in the two solids and still have the same total energy in each. Each of these options is called a microstate. For 6 quanta of energy in solid A and 2 in solid B, there are 9,702 microstates. Of course, there are other ways our 8 quanta of energy can be arranged. For example, all of the energy could be in solid A and none in B, or half in A and half in B. If we assume that each microstate is equally likely, we can see that some of the energy configurations have a higher probability of occurring than others. That's due to their greater number of microstates. Entropy is a direct measure of each energy configuration's probability. What we see is that the energy configuration in which the energy is most spread out between the solids has the highest entropy. So, in a general sense, entropy can be thought of as a measurement of this energy spread. Low entropy means the energy is concentrated. High entropy means it's spread out. To see why entropy is useful for explaining spontaneous processes, like hot objects cooling down, we need to look at a dynamic system, where the energy moves. In reality, energy doesn't stay put. It continuously moves between neighboring bonds. As the energy moves, the energy configuration can change. Because of the distribution of microstates, there's a 21% chance that the system will later be in a configuration in which the energy is maximally spread out. There's a 13% chance that it'll return to its starting point, and an 8% chance that A will actually gain energy. Again, we see that because there are more ways to have dispersed energy and high entropy than concentrated energy, the energy tends to spread out. That's why if you put a hot object next to a cold one, the cold one will warm up and the hot one will cool down. But even in that example, there is an 8% chance that the hot object would get hotter. Why doesn't this ever happen in real life? It's all about the size of the system. Our hypothetical solids only had 6 bonds each. Let's scale the solids up to 6,000 bonds and 8,000 units of energy, and again start the system with 3/4 of the energy in A and 1/4 in B. Now we find that the chance of A spontaneously acquiring more energy is this tiny number. Familiar everyday objects have many, many times more particles than this. The chance of a hot object in the real world getting hotter is so absurdly small, it just never happens. Ice melts, cream mixes in, and tires deflate because these states have more dispersed energy than the originals. There's no mysterious force nudging the system towards higher entropy. It's just that higher entropy is always statistically more likely. That's why entropy has been called time's arrow. If energy has the opportunity to spread out, it will.
Yes. No, both.
Entropy is something that it is
Pardon? Okay.
entropy. When it is hot, it is concentrated. Low, it is concentrated. When it is high, it is going to spread out.
I didn't get you.
ఇప్పుడు లో టెంపరేచర్ ఉంటే అది కాన్సన్ట్రేటెడ్ గా ఎక్కువ హీట్ గా ఉంటుంది. ఎక్కడైతే హై టెంపరేచర్ ఉంటే స్ప్రెడ్ అవ్వడానికి ఎక్కువ ఛాన్సెస్ ఉంటుంది. దాన్ని ఎనర్జీ స్ప్రెడ్ అవుతుంది.
Yes. Anyone understood? Anyone? Still, Bhavesh, you have to tell something. We have seen 5 minutes video. Some from somewhere, some point. Correct only. Concentrated energy, lower entropy. When it spread out, higher entropy. Okay, but it is not making us to sense to understand. Okay, who will tell? Can you please raise your hand? Who will tell what is the explanation of this video so that everyone can understand this from your explanation? Anyone please raise voluntarily? Anyone? Yes, very good. No problem.
Basically, entropy అంటే నార్మల్గా డిజాల్వ్ చేస్తాం అనుకుంటాం. కానీ ఇప్పుడు మనం క్రస్టరైజ్ వాటర్ తీసుకుంటే మనం డిజాల్వ్ తీసుకుంటే క్రస్టరైజ్ అనేది ఎంట్రోపీ ఎక్కువ ఉంటుంది అనుకుంటాం. కానీ అది కాదు, వాటర్లో ఎక్కువ ఎంట్రోపీ ఉంటుంది. సో కరెక్ట్గా ఎంట్రోపీ మెజర్ చేయాలి అంటే ప్రాబబిలిటీ, ఎనర్జీ ఆఫ్ ప్రాబబిలిటీ తీసుకుంటాం.
కరెక్ట్గా డిసార్డర్నెస్ అర్థం చేసుకోవాలి అనుకుంటే ఈ యొక్క ఆ ఎగ్జాంపుల్లో చెప్పినట్టుగా డిసార్డర్నెస్ అనేది కరెక్ట్ మెజర్మెంట్ కాదు. ఎందుకంటే క్రష్డ్ ఐస్ క్యూబ్స్లో డిసార్డర్ ఎక్కువ అనుకుంటాం బై విజిబుల్, బట్ రాంగ్. అంటే డిసార్డర్నెస్ అనేది కరెక్ట్గా మెజర్ చేసే క్వాంటిటీ కాదు, మెజర్ చేసే థింగ్ కాదు. అంటే అది కరెక్ట్ కాదు. ఆ టర్మ్ అనేది ఎంట్రోపీ అనగా డిసార్డర్నెస్ అనే టర్మ్ అనేది చాలా టైమ్స్ కన్ఫ్యూజ్ చేస్తున్నట్టు అన్ని విషయాల్లో అది మీనింగ్ కరెక్ట్ కాదు. ఓకే,
ఎంట్రోపీ ఇప్పుడు మెజర్ చేయాలంటే క్వాంటా అంటే ఎనర్జీ స్టోర్ క్వాంటా అంటారు, దాన్ని బట్టి తీసుకుంటారు. సార్ ఇప్పుడు ఎంట్రోపీ ఎట్లయితే హై ఉందో ఎనర్జీ అనేది కాన్సన్ట్రేటెడ్గా ఉంటుంది. అది ఎంట్రోపీ అనేది లో ఉన్నప్పుడు ఎనర్జీ అనేది కాన్సన్ట్రేటెడ్గా ఉంటుంది. ఎంట్రోపీ అనేది హై ఉన్నప్పుడు ఎనర్జీ అనేది స్ప్రెడ్ అవుట్ అవుతుంది. సో దీన్ని బట్టి
సో ఇంకెనీవన్ వెరీ గుడ్. బట్ ఎనీవన్ ఇంకా ఎవరైనా అర్థం వీడియో 2 times చూసారు కదా వీడియో, ఎవరైనా చెప్పగలుగుతారా? జస్ట్ ఎక్స్ప్లెనేషన్ చెప్పగలుగుతారా? లాంగ్వేజ్ నాలెడ్జ్ అయితే ఏ లాంగ్వేజ్ అంటే నేమ్ యువర్ గుడ్ నేమ్ ఈశ్వర్. ఈశ్వర్, యు వాంట్ టు సే సంథింగ్? Okay, so yeah, so we'll discuss in the next class. Okay.